So in Unit 5, we discussed the very notion of representation. And we considered various ways in which one might choose to represent things in the world using specific numerical patterns. The net talk example was very important because it showed us a principled reason why we might choose a localist representation in one place, that was English orthography, and a distributed representation of a specific engineered kind. We built it for the phonological output. Now, we were drawing there on a host of knowledge and a theoretical framework developed within linguistics in the field of phonology. So we had lots of reasons to choose the output representation that we did. Those forms of representation had proved their merit in many years of the study of human languages. As well as designing representations like that, a popular approach these days seeks to discover the representations through various forms of engineering in which we don't determine what the distributed representation that will feature in the network is, but rather we use techniques to induce such representations. And to many people, this seems like an act of discovery, as if one were going through a pile of stuff one just found in nature, and lo and behold, there are representations. In this unit, we are going to look more critically at that, and we're going to find out that even when representations are discovered in this sense, in a data set, they are in no sense objective. And treating them as such is a social danger. We'll discover some quite powerful techniques for taking an unruly data set, reducing its dimensionality so that specific kinds of similarity relationships are brought out. And having such a condensed representation provides us with a powerful means of transforming that into other representations within the cascade of a network. We looked at one particular problem, which was the problem of location invariance in a pattern. We had patterns with 3 ones in a row, and we had to engineer a network that could spot this kind of pattern. That was dealing with a particular kind of invariance, and there are many other kinds of invariance one might address. And considering these difficulties serves to motivate the search for techniques that will automatically discover features rather than deciding on the basis of theory what the features are. So let's take a very classical problem that's been around since the early days of neural networks, which is getting networks to recognize handwritten characters. So there's a crude handwritten letter J, which might feature as input to a network which was tasked with recognizing this as a J rather than any other letter. As it stands, to me it's a J. I drew it as a J, but it's actually just a bunch of numbers. It's a bunch of red and white squares, which can be represented numerically. But one could build a network and ask it to recognize this as a J. And the solution we adopted the last time suggested that hidden units might usefully restrict their connections to a small part of the input field. So here you can see I have suggested that a hidden unit in this network might look down on only a part of the input field, and this part would contain part of the horizontal cross-stroke at the top of the letter J. But when we encounter letters written by hand in the wild, they vary a whole lot. They are really messy. So J's come in many shapes and sizes, and if we had a very fixed idea of what a J was, it might be difficult to accommodate all these variations on that theme. So in a sense, we're engaged in a kind of a quixotic quest to find the essence of a J, given that J's vary not randomly, but a great deal. So what would one look for in a J? Well, the first J we looked at had a nice well-defined crossbar, a downstroke, and an uphook. Those might be useful features for recognizing other J's, but as we just saw, not all J's will have exactly those. So one might develop a stock of features which are found in the letter J. One might adopt a probabilistic attitude and suggest that the more of these features we find, the greater the likelihood is that we are dealing with a J as opposed to any other letter. This is the kind of approach that we're going to explore now, where we don't know in advance what the features are, but we use the variation in the data in order to inform us as to what the most useful features for our task of categorization or recognition are. So we've got a quite general problem, which is to discover representations in a specific problem domain that act as desired given our task, which is identification, classification, or any other task we come up with. And a certain degree of craftiness is required here. One technique that has been very useful goes by the name of autoassociation. Autoassociation is a very simple idea, and it turns out to be a powerful way of taking a lot of raw data patterns, let's say a lot of handwritten J's transformed into pixel arrays, and developing a more concise, compressed representation, that is, using fewer numbers to represent these, but in such a way that those numbers more clearly make evident the features that distinguish the different kinds of things in our database. That seems mysterious, but the idea is very simple. Consider this feed-forward network. It has 4 inputs and 4 outputs. Supposing we gave it what looks initially like a paradoxical task, we wanted simply to reproduce the input patterns at the output. That is, we presented with 1, 2, 3, 4, and we want to get 1, 2, 3, 4 at the output. Now that might seem like a trivial task, but if you look at this network architecture, you'll note that before the input can generate any output, it has to go through the hidden layer. And there are less units at the hidden layer, so we have something of a bottleneck. Now, if this network can be trained to represent to reproduce all our set of input patterns at the output successfully, then we will have generated at the hidden layer a 3-dimensional form of representation that still preserves all the relevant distinctions within our data set. So as long as the number of hidden units is less than the number of input units, which is the same as the number of output units, this is a non-trivial task. And what we're actually doing is we're training this network, not because we want its output, but because we want those hidden unit representations. They will reveal to us what the important characteristics are that underlie the distinctions we wish to draw in our data set. And notice that because we are simply reproducing the input pattern at the output pattern, this is a slightly different form of learning to what we've seen before. Normally, in a supervised learning paradigm, we have input patterns and we have very different output patterns, and we're learning to map from one to the other. Here, our input pattern is simultaneously serving as our target. So we don't have this slightly worrying feature of the superordinate intelligence who knows what needs to be mapped onto what. And that motivates the idea that what we are doing here is discovering something which is inherent in our data rather than dictating an arbitrary mapping. So the way to think about this kind of compression that goes on at the hidden layer is to think of it as a kind of projection. So if we had an autoassociator with 3 inputs, 2 units at the hidden layer and 3 units at the output, the 3 number patterns that constitute our data set can be represented as points within a 3-dimensional space, let's say a hypercube, a cube actually. The 2-dimensional representation means that these have to be mapped down to points within a square. And then from the square, we need to recreate the distinctions. So it's not the case that any arbitrary projection will do. We need to find that projection from the three-dimensional space to the two-dimensional space that preserves the identity of the distinct elements within our data set. So this is one of several techniques of dimension reduction, and we're going to look at two more as well. And what it does is it forces us to group things together that are similar in a principled way. Projecting from 3 dimensions down to 2 dimensions will lose some information. There's no way that it won't lose some information. The manner, the actual projection we use will be very important to select correctly. This is an old idea. You know how to make shadow figures. In shadow figures, what you're doing is making a shape, a 3-dimensional shape with your hands, and projecting it down to 2 dimensions, in this case to make fanciful animal shapes. But in shadow projections, of course, we're interested in making funny shapes. Here what we're interested in doing is finding the right projection that will allow us to recover the elements that were obvious in the 3-dimensional case. So these projections lose a lot of details about the hand, for obvious reasons. We'll be looking to develop compressions, reductions in dimension that leave intact important distinctions in the data set. So the use of autoassociators is like this. We have a data set, and ultimately we're interested in doing something else with this data set, like classification or identification. But we first employ an autoassociator in order to develop representations of the hidden units, which we will then lift off. We will collect those representations and use those as input to another network, which will do our classification or prediction or identification task. So this is a kind of a pre-processing of a data set in order to develop representations which are as perspicuous, which contain and make manifest the distinctions that are important for the task at hand. That's the goal of autoassociators, and we'll be playing with autoassociators in lab.